Good morning, everybody. Thank you for coming to the V20Y session, a comprehensive understanding of the melting process at the subduction zones. Our first speaker is the invited one, Tim C. Grove. He will have 15 minutes.
Thank you, and thanks for the invitation. I'm going to have to move this up here. For those of you who are speaking in this session today, you're going to feel like a deer in the headlights by the time this whole experience is over. It's being taped. I am going to talk today about integrating experimental studies of hydrous mantle melting with numerical models of the temperature, depth, structure in the mantle wedge. And the focus of this talk is in particular going to be on how melting begins right above the slab wedge interface when you have water coming into the base of the mantle and interacting with mantle peridotite. And that's what these experiments that you can see. I have a little slide here making these first authors interchangeable, because Christy and I have both been collaborating on this work, as you'll see in a moment. And we've also been taking other people's numerical models and working with colleagues at MIT to try to understand what the thermal structure of the base of the wedge might look like and how it might control the location of volcanoes. Because the important parameter that we're going to be thinking about today is when you have a volcano sitting here on the surface and you measure the depth to the slab wedge interface, there seems to be a magic range over which volcanoes arrange themselves in subduction zones globally. And the question is, why is that, and can we understand it in terms of the thermal structure differences that we see? So we've done experiments basically from about 750 to 1200 degrees C, and actually 1.2 to about 6 GPa, using piston cylinder and multi-anvil apparatus at the University of Minnesota and MIT, and piston cylinders at MIT. We've taken an undepleted mantle peridotite. For those of you who know the name, it's the Hart and Zindler peridotite. And then we've added water as brucite, and we've done sets of experiments with a lot of brucite, a lot of water, 14.5%, and a little bit, 3%. The runs are very long. They're usually a couple of weeks. On average, they're about a week. This is what an experiment looks like when it goes in. It's just a bunch of powder. That's the gold capsule. That's what it looks like when it comes out. Nice crystals and melt and all kinds of things that we can measure and characterize. And so this is an illustration of the results of those experiments, pressure on this axis, temperature on that axis. The yellow experiments are the ones that I did in 2006. These are Christie's and colleagues at the University of Minnesota that were published in 2012. The important thing that we found is that the vapor-saturated peridotite solvus is defined by this blue line that drops to about 800 degrees C in a very important pressure range at about 2.5 to 3.5 GPa. This is basically the depth range from the surface up below, it's the surface where you have arc volcanoes down to the top of the slab where water-saturated melting of peridotite begins. And that's what we're going to be focusing on today. So this purpose is to kind of map the phase stability and the melting, the beginning of melting right down here at the slab wedge interface onto geodynamic and thermal models. And this is a little cartoon from one of our papers. You actually can find this in these annual reviews of Earth and Planetary Sciences, where they render your diagrams into beautiful artwork that you can see here. We've got depth on this side, distance away from the trench here, and we got a lithosphere, and basically these different colors are colors of either serpentine or chlorite stability. And this region in here is the mantle wedge, and you can see this gray line that goes down there. That's supposed to be altered oceanic crust, basalt plus sediments. Okay, and this is the slab wedge interface. And so there are three vertical sections that are drawn through here, and we just want to take a simple look at the temperature depth characteristics of each one of these sections. Let's look at A first. In A, Over here is the phase diagram with depth and pressure superimposed. And the path A is this path right here, and it starts down here, and you go up towards the surface. This is basically just where melting under vapor-saturated conditions can begin. Oh, my hand's shaking. What happens is, as you ascend from the underlying mantle into the oceanic crust and then into the overlying mantle wedge, the temperature increases until you just barely touch the vapor-saturated solidus, excuse me. And then what happens after that, as you go to shallower depths, is even if you had a drop of melt that you produced here, that drop of melt would crystallize and turn into hydrated minerals again, like that. And so from here down to here, that's where all the interesting stuff happens. Right in the middle here, this path B, this is path B starting down there. You're going to have serpentine and chlorite, and we're going to look at how they might decompose to provide water to drive melting. The reason we're so interested in serpentine and chlorite is that they contain a very large amount of H2O bound in their mineral structures, about 13 weight%. And so what happens in path B is that if water is released by the dehydration of these minerals, basically the water comes up, it hits the vapor-saturated solidus right there, and mantle melting begins. The peridotite starts to melt. That melt will separate and ascend through the overlying mantle by reactive porous flow. As it goes to higher and higher up, lower and lower pressures in the overlying mantle, it gets hotter and hotter. So the water basically dissolves the surrounding mantle. The melt becomes vapor undersaturated, and the melt amount goes up, and that continues up to the highest temperature, shallowest part of the mantle wedge, here shown as the hot nose of the wedge. And then after that, these melts get out and erupt in these volcanoes. This process shuts off down here at path C, where there are no longer any hydrous phases stable, either in the underlying mantle or in the underlying mantle under the oceanic crust, or stable in the overlying mantle wedge. And so we're going to talk about this region and how global thermal models influence those kinds of processes. So here's a recent paper by Syracuse et al. It came out in PEPI in 2010. And all these, there are 4 different situations here that are different starting parameters. This is the one that we're going to talk about. All these beautiful colors are basically the thermal structure mapped along the slab wedge interface in global arc subduction settings, each one for a different arc. And I'm going to show this picture in the next slide. Here it is, taken out and basically superimposed with our phase relations and the phase relations of others. These are the temperature depth traces of the slab wedge interface from Syracuse et al. There's the vapor-saturated peridotite solidus. Here's chlorite stability, and here's serpentine. So you'll notice that there's a gray rectangle here. That gray rectangle partly outlines the range of depths from the surface, where you have an arc volcano, down to the slab wedge interface, where you find volcanoes in these settings. And you can see that, interestingly, this goes from about 75 kilometers for very steeply dipping systems to somewhere around 150 or so for shallow dipping slabs. You can see that there's an interesting convergence here of all these phase boundaries and these thermal structures. So it really does look like melting is happening right near the slab wedge interface. So we're going to just briefly map out 2 different ways that this melting might occur. And this is the first example. Oh, wait a minute. I actually wanted to point something out before I did that. So you'll notice that there are a bunch of paths down here that define sort of the low pressure, high temperature end of this. Those would be the warmer end of the subduction environment. And then there are a bunch up here on the left that would be the cooler end at the slab wedge interface. And so we're going to kind of contrast those 2 settings. You'll also notice down here that this is basically vapor-saturated melting of oceanic crust, that's basalt, and sediment, they both melt to the same thing, basically a rhyodacite. And so they're also in the mix down here in these sort of hot subduction zones. So here we go. This is a warmish subduction zone, and this is a nice graphical representation, I think, of what's going on. The cartoon over here, basically, of a subducted slab and mantle wedge shows two sets of arrows. The first set of arrows that's up here in this legend is that water gets released down underneath the altered oceanic crust because it actually gets hot enough down there that hydrous minerals break down, serpentine, for example, and under the right circumstances, even chloride. So what will happen is you'll actually have free H2O, and if it can get up into the overlying mantle wedge, melting will occur right here at the vapor-saturated solidus. Now, since chloride is stable above the vapor-saturated solidus, you could also have breakdown of chlorite in these situations. And actually, Christy and I looked at this in some detail. It's a little bit hard to render on a little simplified cartoon. And you could have up to a kilometer or so layer of chlorite in these warmer subduction zones above the slab wedge interface, according to these temperature structures. The other important thing I forgot to mention is that we basically use the Cagni-Onckley thermal structure above the slab wedge interface in order to make these thermal estimates. So here's a cool subduction zone, and please pay your attention more or less to the figure on the right, because this is the same cartoon, it hasn't been adjusted. What can happen in these cool subduction zone environments is you can actually have chlorite stable all through the underlying mantle below the altered oceanic crust, and in a layer above the crust slab interface that's essentially up to 8 kilometers thick. And that's a lot of chloride and a lot of water. And in this case, the kind of melting that you would have in these cooler subduction zones is what we would call chlorite dehydration melting, because you might not have many minerals breaking down or a large amount of them in the underlying slab. But what would happen is that you'd have a huge slug of water that would get into the system when you overstepped chlorite stability right here on this blue line, and as soon as that happens, you release free water. That free water immediately says, ooh, I'm above the vapor-saturated solidus, and so you start melting. So you could have two different contrasting scenarios that you ought to be able to see in terms of trace element signatures. Now, more recently, Peter Van Kecken et al. Have been looking at different thermal models, and they really give a contrasting result. And this is one that's actually in a rather cool environment. It's Mariana's like, I believe. And what it says, basically, it's a little bit different rendering, is that you would still have H2O coming out from the slab and mantle, but you wouldn't necessarily have chlorite stable in the overlying mantle wedge. This yellow transition here is where chlorite becomes unstable. That's the vapor-saturated solidus. These are temperature structures. These are down underneath in the mantle, underneath the crust. That is right at the crust-mantle boundary right there, the base of the wedge. And so you can see you still have this very interesting confluence of water, vapor-saturated melting happening right at the base of the wedge. So I'm done. I just wanted to point out that, you know, this is a really interesting opportunity now that we have thermal models for the subduction environment that are getting better and better, and we've got exciting experimental results that we can use to try to understand how melting begins in the mantle wedge, tying petrology and geodynamics together. Thanks for your attention.
Thank you.
Yeah.
Do you have any questions? Do you see any? Cannot see anybody there.
They really can't see you.
Yeah, so just stand up if you have any questions.
It's better than 2 years ago. That's the latter, Mark. Well, you're going to be limited to a fairly small layer, and it's just going to thin out as you go down, just like it's shown in the cartoons. Now, you could imagine. I mean, Peter's new models actually have a very, very different kind of thermal structure right above the slab wedge interface. So I think that these are guides to try to understand what's happening, but I think probably the best geochemical test that we could apply right now to try to distinguish what's going on is to see if we have evidence of fluids coming from fluids that have passed through the altered oceanic crust and sediments, basically slab melts, versus things that are just from this blanket of chlorite getting involved in the melting situation. And you may be asking about that second case, but that's one where I think advection, or dragging chlorite down and out of its stability field after it forms a little bit higher up is an important part of the way I envision the melting to occur. Does that answer your question? I guess. It does. All right, thanks.
Our second speaker is also the invited one, Mark Spiegelman. His talk is hot enough for, I'm not sure how to pronounce that.
Hot enough for you. Sorry.
So, controls and constraints on modeling flux melting in subduction zones.
Thank you. Good morning. So I'd like to talk about work we've been doing on understanding controls and constraints on modeling flux melting and transport in subduction zones. And subduction zone models are actually reasonably complicated, but I want to focus on two fundamental observations that I think every successful subduction zone model needs to have. And they're pretty obvious. The first one is subduction zones are magmatic, and that they produce voluminous, high-temperature silicate melts, and the most primitive of these are basaltic. So this puts a pressure-temperature constraint on the subarc mantle. The second one, which Tim has already talked about, is that pretty much independent of what you put down there, they all come up in the same place. The arc volcanoes are located about 100 kilometers above the earthquakes. We've known this for a long time. What's less obvious is just how hard these two observations are to capture in a quantitative model. And what I want to talk about today is why I think that is and what we need to change to maybe make this better, because this is, I think, the signature of what subduction does. So just to review the observations quickly, the distribution of volcano earthquake depth is very well established here, two independent studies, and very simply, it's 100 kilometers plus or minus 40 to 50 kilometers, and that pretty much gives you the entire range of these things. So we know where they come out. Getting estimates of pressure temperature beneath the arc is much harder because there's issues of fractionation and water content, but here's a rather nice study by Katie Kelly et al. From the Marianas looking at melt inclusions, which do two things. One, they actually give you an estimate of what the bulk water content is beneath there, and it's fairly small, 0.5%, okay? And then given that, you can use the thermobarometer of Lee et al. To make estimates of pressure temperature of last equilibration on there. And what's also nice about this data set is they also include the Mariana Trough basalts. These are Backarc basalts, which are reasonably dry, and so they're morb-like, and so they kind of calibrate this to morb. And the quick takeaway is that when you plot these all up with this thermobarometer, all of these melts fall very close to estimates of the dry solidus, which is basically these lines here. And the point is that's hot. That's 1,250 degrees at 30 kilometers, and it goes up by about 100 degrees per gigapascal, sorry, 1 gigapascal, and it goes up about 100 degrees per gigapascal. So by the time we're here, this is 100 kilometers, it's 1,400 degrees. That's hot. This is consistent with other estimates. Tim had a nice set in his annual review paper, which I squeezed onto this plot here. And again, they fall right in this thing. And this is not Marianas. This is Japan, Cascades, Aleutians, Indonesia, Isubona. And whenever we look at this, the shallow mantle, the deep ones may be cold, but the shallow is hot. Okay, and so just as a target, I'm going to call the hot zone here is basically temperatures between about 1,250 and 1,350 degrees, between 1 and 2 gigapascals, 30 to 60 kilometers. Now, the problem is that you take this region and you ask, what does this look like in thermal models of subduction zones? everything's just a little too cool. And these are cool models. Don't get me wrong. They're very useful for lots of things, but it's very hard to get this. So that region is sort of outlined in red here, to get those temperatures in what the magmas are saying. So just these are a bunch I should have pulled at random. This is the subduction community benchmark, which as a community we decided to put a 50-kilometer conductive lid on top of things, which makes things very cold. That's about 600 degrees. These two are very nice models focusing on seismic constraints and slab temperature structure. And in particular, there's this important idea that the slab gets coupled at about 80 kilometers here, which is important to get the seismic structures consistent. But again, these are a little bit cold. Their maximum temperature in here is about 1,200, similar with this one here. This is that Cagnon model. It's a little bit hotter. It was emphasizing melting, so, and it's hotter for two reasons. One, this coupling point was moved up to 50 kilometers, and the inflow temperature is actually a little bit hotter in here. So this gives it, but all of these are still colder than the estimates from the basalt. These are all kinematic models, in the idea that the geometry of slab and wedge are given by boundary conditions. There's also a set of quote dynamic models which allow subduction zones to form spontaneously. But in this particular one, same idea. Nothing in this whole region here is above 1,000 degrees. Okay, so this should not produce any melts at all. Now, as I was looking through, this is the coolest model I found that I was looking through. And interesting, this gets it right. It has the hot magmas right underneath the volcanoes. Okay, the trouble is it's not terribly quantitative, so it's hard to know what they did. But this is the point. The cartoons get it right. The models don't get it right. And the question is why? Well, one of the things, these are all solid-state thermal models. They don't have melting. They don't have transport. They don't have water. So, you know, maybe having water and flux melting is going to help us. But that's not entirely clear either. It depends a lot on what parameterization you use for wet melting. So here's one. It comes also out of that Kelly paper. So what I need to do in my models, I need an estimate of F, the degree of melting as a function of temperature, pressure, and bulk water composition. This is the one that Kelly did. And so this is, again, from 1 to 3 GPa for half weight percent. This is an undersaturated solid, half weight percent water. That pink line is the dry solidus we saw before. Add water. In this model, there's a little bit of solidus lowering. But even at the dry solidus, this model only predicts about 4% melting. If you want 10% melting, you're going to have to be up here, considerably hotter than the dry solidus. Okay? But this isn't the only parameterization. Here's one. I don't necessarily trust it, but I took P melts and actually added water to it and asked what is the F of T, P, and C for that. And this is sort of interesting. If you actually make it dry, this is for a depleted mantle source. If you make it dry and take potassium out of it, the dry solidus is actually higher prediction than Mark Hirschman's estimate, which is about here. But when you put water in, it puts in this very low productivity tail, which extends all the way down to the water-saturated solidus, which isn't the same as Tim's in this, but I think structurally this is the right idea. So down here, well below these temperatures, I can get about 4%. But again, if I want 10, 15% melting, I need to be close to the dry solidus. That's a hard constraint. And water doesn't necessarily, so water will help you for sure, but there's another issue with it, which is that the source of it, which is what Tim was talking about, is also potentially quite variable. This is a set of diagrams. So this is estimates of where water is released from the slab into the mantle for a very wide range of subduction zone models. And basically the way to look at this is, so they all have this coupling depth of about 80, so there's a big burst of heating event at about 80, so that's where a lot of water comes out. But you can see here, every time there's a jump in this thing, that's where an extra water is added to the mantle. And you can see basically water is contributed everywhere from here to 250. You basically get water anywhere you want. And it's very sensitive to the, oh, this is important. This is very sensitive to the structure of the slab temperature, okay, and plate age. However, the location of the volcanoes is not. There's no correlation between where the stuff comes out and the plate age. So it all comes out in a very narrow band, but this suggests that water can come out, can be produced, entered into the wedge pretty much anywhere. So here's our problem. This is the grand subduction zone modeling challenge. A good model should do two things. One, it should have flux melting produce high temperature magmas, and two, they should all come out about 100 kilometers over the earthquake. And I ask, is that too much to ask? The Earth does this just fine, but we're having problems. So I should say, we've actually done some we're getting better at this. This is probably the best version of this problem so far. This is Cagnon, at least published, 2007. And what they did is, again, they took one of these kinematic thermal models with a temperature-dependent viscosity. They put the coupling point here at 50 kilometers. They had a reasonable mantle adiabat, so that the hottest material coming into this model is actually about 1,500 degrees. And then they added to that a simplified fluid flow model, where they basically said that fluids released from the slab will basically, the only thing that will control their transport is advection by the solid. If it's low permeability, the solid will take this and actually drag it down, and gravity, which will make the fluids basically go vertically. And they used what I think is a rather low permeability for a hydrous fluid, but in this case what happens is it comes out and then it rises pretty much vertically. The water flux is imposed as a Gaussian at a specific depth, but it's not a bad depth. It's sort of the range that Tim was talking about. And they actually do get melting. They have a melting parameterization, again, based on P-melts, and they get about 5% melting right there. But because it's gravity-driven, it basically it misses the volcano in this case. Okay, but this is the one to beat. Can we do better than this? This is what we've been working on. And what I'm going to argue is that, given the structure, if we add a little bit more physically reasonable fluid transport into this, we can change this picture significantly. So what we've done is, this is the next generation set of models. This is I'm not going to talk about it here. Key and Wilson will talk. This is a new modeling system called Terra Firma, sorry, the Transparent Finite Element Rapid Model Assembler, which allows us to explore very rapidly complicated multiphysics models. I'm not going to talk about that now, but if you want to see Kian's talk, it's today at 11. But we're going to use this to basically first recreate, with a few changes, the Cagnon model, and then add one piece of physics to it and see what actually changes. So the thermal model is pretty much the same as we've seen. We use the simplified geometry of a 45-degree slab. Its temperature-dependent viscosity. I used the more recent coupling depths of 80 kilometers to be consistent with the seismics. And the inflow temperature is probably a little cold. It's about 1,400 degrees. And importantly, I've used the thermodynamic models of Brad Hacker to estimate water contents of the slab. And I've been a little cheeky here, is that I've ignored the shallow water here, because that actually in these models tends to come out before it ever gets to the wedge because of this heating effect. The main source of water for this particular calculation is a deep serpentinized layer, which doesn't dewater till about 150 kilometers, and then a slow dewatering of the gabbro, which comes out over a range down to about 250 kilometers. So we're going to take this model. And just in terms of resolution, to get these thermal models right, you need really extreme resolution, and this Terra Firma allows us to put really quite fine, unstructured meshes on these things, but we won't talk about the numerics. Okay, so we take this thermal model, we take these dewatering points, and I should say, this is cold too. This is always going to be cold. It's that's sort of the 1,200. It's again, it's in the 1,000 to 11 category here. But in this case, the fluids come out here and here. You can see them. This is the porosity. And because I use a slightly higher permeability, not that high, this only says that the fluid velocity is moving 50 times faster than the solid velocity. That's not high permeability. And you get these low, basically vertical transport of very distributed low water contents that obviously don't make it to the volcano. I want to change one thing. The physics in here, as this fluid comes up, it's trying to sort of work its way through this. It doesn't know anything about the rheology of this upper plate, the fact that, or the slab itself, that there's this sloping, increasingly strong layer that it needs to get through. And if you add one, sorry, I forgot to say. And if you estimate the amount of melting from this, with our best parameterization, the melts one, you get 0.1%. So this doesn't produce melt, it doesn't produce in the right place. But if you change the physics with one term, this is what happens. I think that's pretty cool. All right, I think I have to do that again, can I? Let's try that. All right. Okay, so what's happening here is I've introduced another thing which allows the fluid to see the rheological structure of the thing. And so it's basically coming up. It starts to see the strengthening boundary layer. which as it will generate additional pressure gradients which deflect it and drive it up to the shallowest, hottest part, which happens to be underneath the volcano. All of this bubbly stuff in here, these are under-resolved solid porosity waves, which are natural consequence of, if you want this effect to happen, these are going to come with it because it's the same piece of physics. All right, so we're this is the same model with one difference in the physics. In terms of degree of melting, though, this is getting here, it's about 16% melting using that parameterization, and how conveniently right underneath the volcano. Now, this is my best one right now. But the other thing is this physics has two things. It concentrates fluids and changes the local bulk water content to actually push it up to allow more wet melting. So I'm almost done. Lots of caveats. This is a very simple model for illustration. It has an idealized geometry. All these wet melting calculations are post-processing. They're not coupled to the thermal structure or flow. I'm not allowing rehydration reactions yet. I have no coupling of feedback of solid flow into fluid flow, and I'm sure there's something you can choose to complain about. The important part is, though, that this new software, Terra Firma, allows us to very easily play with a lot of these parameters and explore lots of these couplings and understand what's important. The thing that is important, in a way that's manageable and transparent, what's actually important, though, is in the end, if we've done this right, none of this should matter because the output is robust, that it shouldn't depend on, it shouldn't be sensitive to the details. So that's the takeaway. There's a lot of uncertainty in physical and thermodynamic models of wet melting and transport. The Earth doesn't care. It always produces high temperature basalts with small variability in arc locations. And I claim that a similar robustness should be a requirement of any subduction zone model that you're going to claim success on for magmatic melting. And as a first cut, I'm claiming that if you work a little bit harder on certainly the fluid flow and transport, that you may have feedbacks that actually lead towards this kind of robust behavior. And I'll stop.
Sorry that we have to move to another talk. So our third one is also the invited talk given by Doug Wins. The title is Imaging Metal Melting Beneath Island Arcs at Backarc Spreading Centers.
This is advanced. Okay. Well, I want to thank the conveners for inviting me to have a chance to talk about the imaging some of these processes. Wow, those lights really are bright. So basically, I'm going to be talking about the results of two large seismic experiments, mantle imaging experiments. One was funded by Margins in the Mariana Arc, and that had it was a joint U.S.-Japanese project, and we deployed 58 ocean bottom seismographs and some land seismic stations. We had some trouble with some of the U.S. OBSs on that one, but are still able to get some reasonable results. And in a more recent study that we're still working on in the Lao Backarc that was funded by the Ridge program. And I should say that I think these are sort of ideal areas to try to image magmatic processes in the mantle, because in both areas we have active Backarc spreading centers that are adjacent to the arc, and so we can look at the relationships and contrast the imaging of those two different magmatic systems. And we also have very active seismic slabs in terms of earthquake activity that give us many sources to do this imaging. So I'm just as a preview, I'm going to convince you, or try to convince you, that mantle seismic imaging allows us to delineate the melt source regions beneath the arc in the Backarc spreading center, this allows us to kind of constrain the spatial locations where the melting is actually happening in the mantle. And then the hope is that as we go along, then we can say things about melt porosity in the mantle and help to constrain some of the models that have been discussed earlier this morning. So just to go to the Mariana study. So this is a seismic tomographic image of P-wave seismic velocity across the Mariana Arc and Backarc. And sort of some of the things to note is that we do image the very slow velocity anomalies beneath the arc and the Backarc spreading center separately. And they're separated by a relatively fast region, which is sort of a refractory lithosphere, I believe. There's maybe some interaction between these zones at a depth. If there is an interaction, it'd be at depths of like 70 to 100 kilometers there. The arc has the maximum anomaly is about 60 or 70 kilometers depth, whereas the Backarc, the maximum anomaly is more like about 20 kilometers depth. This is consistent with the thermobarometry by Kelly et al. That was mentioned in one of the earlier talks that give a deeper source region and sort of precisely what the depths that we're imaging here for the arc magmas as compared to the Backarc magmas. The Backarc signature seems to be somewhat stronger in terms of the seismic anomaly than the arc signature, and that's something that we'll also see in the Tonga or in the Lao Basin area. And I just want to point out also we can image pretty much the same anomalies then with seismic attenuation. And this will, I believe, as experimental work gets better on some of the seismic properties of magma or of partial melt systems, will allow us to put better constraints on some of the material properties. But we indeed see the same anomalies there in the seismic attenuation, and once again the Backarc spreading center anomaly is stronger, even though it's more poorly imaged. There's much less ray coverage as we get to the Backarc here. And I just wanted to also, while we're talking about the Mariana, mention that there has also been a really nice MT study that was done also as a joint Japanese-U.S. project. And this is the image that they got from the MT study of the Mariana Arc. And I guess the sort of remarkable things are that even though they had a pretty high density of OBEMs near the Mariana Backarc spreading center, you don't see a high conductivity or low resistivity region associated with the Backarc spreading center, whereas you do see some low resistivity or high conductivity area at depths of about 100 kilometers near the arc region. So this will also place constraints on these systems. Just to get to some of the newer work, this is some work by my graduate student Sean Way, and he'll give a talk on Friday afternoon on this work. But basically, this is a surface wave study of the Lao Basin. And so it has some differences from the previous images in that it has probably better depth resolution but poorer lateral resolution than some of the previous studies. But you can see that we're also imaging the spreading center, particularly the spreading center anomaly, very strongly. These velocities here at about 60 kilometers depth beneath the central Lao spreading center are extremely low, on the order of 3.5, 3.4 kilometers per second, almost the lowest seismic velocities imaged anywhere in the Mantle in the world. Sort of a remarkable thing here is that we see this dipping zone of very low seismic velocities dipping to the west, suggesting that some of the melt production is probably not occurring immediately beneath the spreading center, but is instead occurring somewhat to the west, perhaps on a rising limb of a convective pattern as material is sort of sucked in from the west towards the spreading center. Other sort of interesting things, this is the central Lao spreading center here, and then this is the eastern Lao spreading center here, and it does look like the anomaly is sort of centered beneath the central Laos spreading center, which is propagating southward. So some of the ridge tectonics there may be linked to the deeper mantle processes. And then we also are working on attenuation structure of the Lao Basin, and this is a 2D inversion, but it also shows extremely large seismic anomaly beneath the eastern Lao spreading center, maybe slightly to the west in the upper 100 kilometers or so. And another issue here is that the anomaly associated with the Tonga Volcanic Arc, the Tofua Arc, is actually relatively minor. This may perhaps be related to the arc. This is sort of preliminary work, and we're hoping that the resolution will increase a lot as we go to a 3D inversion there. But once again, it seems like the primary anomaly is associated with the Backarc spreading center. I'd like to convince you that what we're actually looking at here is the melt region in the mantle. And evidence for that is that the strongest anomalies are concentrated beneath the Backarc spreading center, and to a lesser extent the volcanic arcs. The anomalies are way too large to result from temperature effects alone. If we put in the mantle temperatures that are inferred from petrology and use relationships such as Fowle and Jackson, or really any other relationships you want to use, you'd predict shear wave velocities of about 4, and we're observing velocities down to about 3.5. The strongest anomalies are at the depths where we expect melting, 20 to 100, or in some cases 20 to 70 or so kilometers deep. And in Mariana, even the anomaly depths correspond very well to the thermobarometry of Kelly et al. So I think there's no question that we're really observing the melt in the mantle. It has been suggested that we might be, in the mantle wedge, you might observe the seismic effects of water instead of the effects of melt. And I think there's really two lines of evidence that suggest that's not true, that we're really not to first order, at least, imaging water. And that one evidence there is that the capacity for storing water in mantle materials, normally anhydrous minerals, is very small at these shallow depths. And then if you do a calculation, there aren't really good relationships between mantle water and seismic velocity, but if you use, for example, Corrado, you would get only a modest decrease in seismic velocity for these small water contents. If you have more water in the mantle wedge is hot, and so these higher water contents would form an aqueous melt, which is what we observe, I think. So we're observing melting. I guess one other thing is that if we just look at the Backarc spreading centers and their inferred water contents, the ones that have the largest seismic anomalies, such as the central Laos spreading center and the northern eastern Laos spreading center, have relatively modest water contents, whereas the Velafar Ridge, the southern part of the Lao system, which has a very high water content, has a much more modest seismic anomaly. So we're really observing melt and not water. Now, what are we actually looking at? And I would say that we must be imaging different amounts of melt porosity or different geometries of the melt in the mantle rocks. Both the melt porosity and the geometry at which the melt forms in the rocks will affect the seismic results. And unfortunately, the seismic effects of melt are not well quantified by experiments. But there is geochemical evidence that the melt porosity needs to be small, and this is a somewhat controversial topic, but U-series disequilibrium measurements, for example, would suggest that we only have very small amounts, like less than 0.1% or so of melt porosity in the mantle. But I guess one thing I'd like to remind you is we are not observing for the rate of melting, we're not observing the extent of melting. We would be observing just the melt porosity, which is a property that's related to the melt production and transport. I'm going to have to go through some of this pretty fast, but there is some experimental evidence that even very small amounts of melt will have a very large seismic effect. There there's problems with these experiments, but they both suggest sort of the same thing, which is that the experiments on olivine and the experiments on analog materials suggest that even a very small amount of partial melting, such as 0.25% or even 0.1%, will have a significant effect on seismic attenuation and thus on seismic velocity. I'm going to have to skip through this pretty fast, but basically this was a calculation that I did just using the Jackson et al. Experimental relationships and the inferred temperatures from geochemistry and petrology for the temperatures, Mantle potential temperatures in the Lau and Mariana. And for both regions, we get something like 0.1% melt porosity from the attenuation measurements. This is just some results from a recent paper by Matsuno et al. Suggesting that their EM measurements in the Mariana Backarc show that the amount of melt content in the mantle must be less than 1% melt porosity. And finally, I'd just like to point out that one really interesting thing that we're finding is if we look at the seismic tomography along the eastern Lau spreading center here in the Lau Basin, and that's shown here on its side along that line DD prime, we see a much larger seismic anomaly in the north than we see in the south. Well, there's a huge geochemical variation along that and petrologic variation along that arc as the Backarc approaches the Tofua arc and approaches the slab, where you go from go from basalt here to more silicic as you go south due to the effect of water. And we're seeing a much smaller seismic anomaly to the south, and this must be related to this transition along the eastern Lau spreading center, probably due to the fact that you're flushing the southern region with water, which may reduce the melt viscosity and cause the melt to be extracted much more efficiently. But my student Sean Wei will talk further about this on Friday afternoon for those of you that are still around. So these are the conclusions, and you can read them because I'm over time.
Thanks, Doug. I'm afraid we don't have time for questions, but it was a great talk. Next up, we have Haiying Gao, who will be presenting seismic evidence for 3D decompressional melting, the Cascadia subduction zone.
Thank you for the introduction. So in this talk, I will present some seismic imaging at the Cascadia subduction zone and then discuss the implications. As we know, at subduction zones, there are 3 possible melting processes. The first one is flux melting from the dehydration of the subducting slab. The second one is the decompressional melting induced by slab subduction. The third one is subducted melting of subducted sediment at the top of the oceanic crust. As shown on this figure, these 3 melting processes predict different spatial patterns of melt generation. So the question is, if we are able to distinguish these 3 patterns with seismic imaging. At the Cascadia subduction zone in recent years, there is a huge increase of seismic stations, which provide a good opportunity for a high-resolution velocity model. So the Cascadia subduction zone is relatively young and warm. It has the shallow dehydration, which result in the dry arc. As defined by geochemical signatures, the quaternary volcanic arcs are segmented along strike into 3 groups, defined as the Southern, Central, and Columbia group. Just keep the definition in mind, since I'm going to use the 3 segmentation in the following discussion. So in this talk, my goal is to understand the melting process with the seismic method by constructing a velocity model of the crust at the upper mantle. Compared to previous seismic tomography, I implement 3 ways to improve the model resolution. The first way is I include all the possible broadband seismic stations in the Pacific Northwest, including the Earth Scope Transportable Array or the permanent stations at a portable array, and also I include the Canadian stations beneath Vancouver Island. The second one is we implement a modified normalization method which result in very high resolution, high quality empirical green functions from ambient noise from period 7 to 200 seconds. That is much longer than previous studies. As shown in this figure, this is the empirical green functions from one station to all the others at the shorter and longer period, which give us very pretty empirical green functions. The third one is I use the full-wave ambient noise tomography method, which is a more accurate seismic theory. So just a quick comparison of the initial reference model and the updated model. What you see is the x-axis is the station between 2 stations. The y-axis is the phase delays between the observed and synthetic waveforms. We measure the phase delay times at multiple frequency band, considering that Rayleigh waves have different depth sensitivity at different periods. So the black dots are the phase delays from the initial reference model. You can see at different period, there is a positive or negative linear trend of the phase delays on station distance. This means the velocity model is either too fast or too slow at that depth range for the real Earth structure. The red dots are from the updated model. Can see the linear trend is better corrected, and the data is less scattered. Move to the absolute shear wave velocity model. Here I show the 3 depths shear wave velocity model in the upper mantle from 65 kilometer to 110 kilometer. The slab interface from 20 to 100 kilometers are shown here for reference. Also, the white triangles are the along strike cascade volcanoes. So the most striking figure in this seismic imaging are the low velocity volumes at the Backarc along strike, especially at 94 kilometer. So as shown in this figure, they are segmented and especially correlate very well with the 3 segments of the volcanic arc. In the bottom, just a quick view of the resolution test at the corresponding 3 depths. Can see because of the damping and smoothing parameters, we are not able to fully recover the amplitude of the velocity, but the velocity perturbation pattern are well recovered. Just to take a close look at the Backarc low velocity volumes. This is at 94 kilometer. As we see, these Backarc low velocity volumes are far away from the arc. It's about 200 kilometers away. And the central one is the biggest and the lowest in velocity. Just draw a few profiles crossing the 3 low velocity volumes. And the lower right shows the south to north profile crossing all the 3 low velocities. The dashed line is the projected plate interface. As you can see, for the west-east profiles, all crossing these 3 low velocity volumes, we see the low velocity volumes at depths 80 to 110 kilometer, which is just far behind the arc. Also show from the south to north profile, as we see they are segmented along strike. So the question is, what caused the Backarc low velocity volumes? Are these fundamental subduction process or it is caused by small-scale convection. Come back to the figure of the melting process. Compare this schematic figure at our seismic imaging. We can see that the low velocity, the pattern of the Backarc low velocity volume is consistent with the slab-induced decompressional melting. However, because of the model resolution for small-scale structure, we cannot exclude the existence of the small-scale dye pairs caused by the melting of the subducted sediments. Another evidence for the to support our explanation is the lab experiment, which considered the slab rollback at a small Backarc extension. So what you are looking at is half of the subducting slab. This is the central wedge. This is the edge of the slab. The color scale shows the magnitude of the slab-induced melting. As you can see, the magnitude of the upwelling is strongest in the center of the slab, and then gradually decrease to the edge of the slab, which is consistent as what we observed for the low velocity, where the central wedge being the biggest and the slowest. But the difference is the decreasing trend from the experiment is gradual, and our three low velocity volumes are segmented. So what caused the segmentation of the low velocity volumes? So small-scale convection has been proposed in the upper mantle subduction zone, and it can really modulate the large-scale subduction zone. In the Honshu subduction zone, northeast Japan, from the seismic tomography, they image the low velocity volumes beneath each volcano cluster, which is periodic at no low velocity between the gap of the volcanoes. Small-scale convection has been proposed to explain the hot finger structure. By comparing the Cascadia and the Honshu subduction zones, we can see that the low velocity volumes in the Cascade Backarc has much larger scale compared to the Honshu subduction zone. However, the along strike variation of the low velocity volume indicate existence of small scale convection, which require low velocity viscosity low viscosity mantle wedge. The seismic pattern can also be disturbed by other small-scale convection, like shown on the lower right, the small-scale thermal convection. So the second question is, what caused such a low shear wave velocity in the Backarc? So this figure is based on Doug Wynn's from two publications. What I'm showing is the y-axis is the depth, and then the x-axis is the shear wave velocity. The red lines are from the low basin, and the black line is from the 0 to 4 million years Pacific upper mantle as reference. So the three blue lines are the three point velocities above the beneath the Cascade Backarc. By comparing these three blue lines with the red and black lines, we can see that the Cascade Backarc velocities has deeper and lower shear wave velocity compared to them. This indicates existence of melting at this depth. As introduced by Doug, the shear wave velocity can be reduced by water, temperature, and melt. So how about temperature and water in the Cascade Backarc? This is just a quick example to show the relationship of temperature, shear wave velocity with depth. So as we can see, to reduce the shear wave velocity to 4.0 kilometer per second at about 100 kilometer, we need the temperature to be at least 1400 degrees. This is much higher than the Backarc velocity, Backarc temperature in the Cascade. So the temperature alone cannot lower the shear wave velocity to as low as 3.6 kilometer per second at 100 kilometer. The second one is the water content in the cascade. This figure shows the water flux content in the whole subduction zones. This is a figure by Peter Y. Kenken in 2011. By comparing cascade with other subduction zones, we can see that the water content at the subduction zones decrease very fast landward. So the water were dehydrated at a much shallower depth compared to the northeast Japan. So by comparing the temperature water content, our conclusion is the low velocity volume at the Backarc is a result from the combined effect of a hot upper mantle wedge with existence of partial melt. The take-home message from this talk is we image 3 segmented low velocity volumes in the Backarc at the cascade, which is segmented and especially correlate very well with the segmentation of the volcanic arc. The pattern of the seismic loads at the Backarc is consistent with slab-induced decompressional melting. However, the segmentation along strike indicate existence of small-scale convection. Thank you.
Thanks, Haiying. I think we'll just keep moving to stay on schedule here. Our next talk is by Nick Harmon, and he'll be discussing 3D shear velocity structure of Costa Rica and Nicaragua from teleseismic and ambient noise Rayleigh wave tomography.
Okay.
Yeah, here's the pointer. You can use this to change.
Okay, cool. Thanks again for having me speak. So I'm going to talk about the 3D velocity structure of Costa Rica and Nicaragua from surface waves. So I recently got love waves up and going, so I'll show more recent results. But I'd like to take a minute to thank my co-authors on this, Marielle Salas, Kate Riker, Jeff Abers, and Karin Fisher. So Costa Rica is a great place to look at subduction zone processes because there are really strong long arc variations in a variety of geologic, geochemical, and geophysical observations. For example, Nicaragua is underlain by Paleozoic continental crust, whereas Costa Rica is underlain by Mesozoic oceanic crust, which is thought to maybe have been part of the Caribbean large igneous province. The arc geochemistry exhibits global extremes in terms of sediment markers such as barium lanthanum. So in Nicaragua, you go from a global high in the north to basically the background mantle in Costa Rica. And the long arc there as well, there's a 50-kilometer jump in Nicaragua to Costa Rica. And also some very nice work by Kate Riker and Ellen Syracuse showed that there are strong VP-VS high anomalies in Nicaragua and high attenuation in Nicaragua relative to Costa Rica, which was interpreted as maybe being due to higher fluid fluxes or perhaps due to slightly higher temperatures in Nicaragua. And just to help orient you for things that I'll be talking about later, the geologic structure of the region. The Nicaragua depression is located beneath Lake Managua and Lake Nicaragua, and the Chortis block is beneath Nicaragua, and the Chorotega block is beneath Costa Rica. And then the suture is thought to lie somewhere south of Lake Nicaragua, but it's kind of obscured by sediments and volcanics. And I'll be using data from the toucan array, which is shown by these red triangles. And just a preview of the different transects we'll be looking at later. So the goal is to image crustal structure across the region using short period Rayleigh and love waves from ambient noise. We will use long period information from Rayleigh waves to image mantle structure of the wedge and slab. The nice thing about doing both studies and combining them is that the short periods really give you good constraints on the crustal structure, which prevents you from mapping that structure into the mantle anomaly. So you should get a better resolved 3D shear velocity model by combining the two in the inversions. And the other thing about looking at Love and Rayleigh waves and Love waves is it allows you to examine radial anisotropy because of the different sensitivity for horizontally polarized shear waves versus vertically polarized shear waves. This is just an example of the data. So on the left here, I'm showing the vertical component noise cross-correlation functions, and you see move out and relatively good signal to noise. Here's the transverse component cross-correlations. And then finally over here, I'm just showing an example of dispersion from a teleseismic event at Station Zappa. So pretty good data quality in general. For ambient noise, our assumption of a uniformly distributed sources is good for 20 to about 10 seconds, and in about 7 seconds it becomes pretty heterogeneous. And what I'm showing here is just beamformer output to show you where the energy is as a function of azimuth and slowness. And then on top of that, I've plotted in black and white dots, which are color-coded by signal to noise, is just the phase slowness measurements for each cross-correlation. And you can see there's a good correlation between the observations of the NCF and the beamforming, so they agree pretty well. So that's for Rayleigh waves. The Love wave noise distribution is a little bit less homogeneous. So in this case, you can see that the northeast, there's the energy is kind of petering out, but northwest and southeast are pretty good for 20 seconds, going down to 10 seconds as well. Probably good enough for government work. But the interesting thing is when you contrast this with Rayleigh waves, using a similar data set, we see that the Rayleigh waves are better distributed, which probably says something about how the microseism is being converted from Rayleigh wave energy to Love wave energy. So the method I'm using for the teleseismic Rayleigh wave inversion is the two-plane wave method of Forsyth and Lee, and we use 2D phase and amplitude sensitivity kernels. And this is just showing you the nodal parameterization and the earthquake distribution that we used. For the ambient noise, we use phase sensitivity kernels, and this is the ray path coverage that we had for the Rayleigh waves, and this is just the nodal parameterization that we used. And it's a three-step process. First, we determine the best average phase dispersion curve for the region. We do a 1D shear velocity inversion. Then we move up a dimension and do 2D phase velocity maps. And then we use the phase velocity maps at all periods to invert for a three-dimensional shear velocity structure. So this is just the result from the 1D inversions. So here's the dispersion curve. So from 10 to 20 seconds, we use ambient noise, and then we stitch it together with the teleseismic information from 22 to 167 seconds. And this is our, it's a well-constrained 1D shear velocity model for the crust and uppermost mantle. We can compare that to the Love wave ambient noise shear velocity model. So the dispersion curve for Love waves in the crust are down here. This is the sensitivity kernels for Love waves, and most of our sensitivity is in the upper 50 kilometers or so. But we can see even in this simple 1D average over the region that the Love wave shear velocity is significantly faster than the Rayleigh wave velocity, which indicates that there's probably pretty strong radial anisotropy in the crust in the region. Before I get into the 2D phase velocity maps and the shear velocity model, I'll have a brief word about formal resolution. Resolution in general is pretty good for the teleseismic study, which is shown down here, and this is the resolution for the ambient noise study. The resolution for the ambient noise study is a little bit worse because we use a finer node spacing, so you have to average 2 or 3 nodes to get a unique piece of information. We can describe that in a slightly different way using something like resolution length, which is the amount of spread a point anomaly would spread out to adjacent nodes, which gives you an idea of the length scales that are resolvable. And so in the teleseismic study, our resolution is about 100 kilometer length scale for an anomaly. For ambient noise, it's a little bit better, so from 50 to 75 kilometers. But in general, anything that's on the order of 100 kilometers is probably interpretable, and anything that's shorter length scale than that is probably just an artifact. And then finally over here is the amplitude bias, which is the percent difference between an input and output velocity anomaly, which gives you an idea of how well you'll recover it. And so we'll probably be within 10 to 15% of our input to the true model. So that being said, here's the short period Rayleigh wave phase maps. And there's a couple of general trends. So at the shortest periods, 10 to 12 seconds, we see very low velocities beneath the arc in Costa Rica and Nicaragua. And then we see high velocities in the Backarc, in the metamorphic geology. And then as we go to longer periods, the low velocities beneath the arc persist, but then the fast velocities begin to focus beneath the Nicaraguan depression between Lake Nicaragua and Lake Managua. And then similarly, we have a similar picture from the love waves. We see low velocities beneath the arc, and then a higher velocity back arc region. And when we go down to the Rayleigh wave phase velocities at 33 to 90 seconds, we see a low velocity anomaly consistently beneath Nicaragua and relatively higher velocities beneath the Costa Rican arc. And then at greater depths, we see, and I'll also point out that we see this high velocity region offshore. And then at the longer periods, we see this high velocity region starts to migrate towards to being located beneath the arc in this case. I'll give my interpretation of these when we start talking about the shear velocity, because now we have some idea of where these anomalies occur at depth. And so just working our way down through the crust, we see low velocities at shallow depths. This is a depth average, which is, I chose to present it this way because it's a well-resolved depth. But we see low velocities beneath the arc in Costa Rica and Nicaragua. And we interpret this as being due to heating of the crust by the influx of magma, and it could possibly also reflect the presence of magma in the crust. And these low velocities persist down through what I would consider crustal depths. I'll also note that beneath the Nicaraguan depression, there's these high velocity anomalies, which I interpret to be thinning of the crustal structure, and adjacent to them are low velocities, which are consistent with thickened crust beneath the Costa Rican arc and also beneath the Nicaraguan highlands and Backarc. When we start moving into the Mantle wedge, we observe a strong low velocity anomaly beneath Nicaragua and relatively weaker low velocity anomalies, which are consistent with the previous work that have showed high VPVS and high attenuation in Nicaragua. And then we also see this blue tabular feature, which we interpret as being the presence of the slab. We have a similar picture for the crust from love waves, although the low velocities beneath Costa Rica are much weaker, which may indicate that there's a stronger radial anisotropy in that region. We can look at this in a transect view, and we see, again, the low velocity anomaly beneath Nicaragua, which is this A to A prime transect, or sorry, B to B prime transect, which goes down to about 3.9 kilometers per second relative to just about 4 kilometers per second beneath Costa Rica. We also see this dipping fast region, which we interpret as the subducting slab. The picture is fairly complicated when you look across strike. So you see a broad low velocity region beneath Nicaragua relative to Costa Rica. And we see a similar crustal structure. We see thickening beneath the Nicaraguan highlands, and again, complicated structure in the Costa Rican line. And so we can map crustal thickness if we choose depth to something like the 4 kilometer per second velocity contour. And that's what we're showing with this. And so we see relatively thin crust beneath the Nicaraguan depression, thicker crust up to 40 kilometers beneath Costa Rica and Nicaragua. What I've plotted here and these symbols at the station locations are Laura Mackenzie's receiver function estimates for crustal thickness. And in Nicaragua, we have pretty good agreement, but in this region, we're a little bit off. But the structure here is quite complicated, so that's not surprising. So in conclusion, for the crust, we see low velocities throughout the arc crust, which we interpret as being due to magma intrusion. The differences between SH and SV suggest there may be strong radial anisotropy. The high velocity crust in the Backarc is consistent with metamorphic basement. Thin crust beneath Nicaraguan arc is possibly due to extension or a thinner accreted terrain, but this may help to explain why there's the jump in the arc segment there. And we see thickened crust in Costa Rica and Nicaragua. And then our low velocities beneath the Nicaraguan arc and Backarc are consistent with previous results. And without any a priori information, we image this lab quite well, which is pretty good for velocity tomography. So thank you.
We have time for a quick question in between presentations. If there's a question, please just holler. I can barely see. Okay. Then our next, thanks again, Nick. Our next speaker is another invited speaker. This is Lauren Cooper, who will be discussing using U-series and beryllium isotopes to reveal the occurrence and relative timing of crustal and mantle processes in the southern volcanic zone of Chile.
So I wanted to thank the conveners for inviting me to give this talk. As you can see, this is a very collaborative project, as seen by the large number of co-authors on this paper. So I'm going to be talking about how we can use geochemistry to tell us about subduction zone processes, and these can be inputs that might be used in these geophysical models. So just to give a brief background of U-series systematics for all the non-geochemists, these are two of the U-series decay chains and the relevant daughter nuclides. And what we're interested in is the parent-daughter ratios, but the activities of the nuclides, where the activity refers to the decay rate. Secular equilibrium exists when the daughter-parent ratio is equal to 1. And then any sort of fractionation events, such as fluid addition or mantle melting, can take you out of secular equilibrium. And then it will take 5 times the half-life of the daughter nuclide to return to equilibrium. And this is particularly important for the radium-thorium system because of the half-life of radium is very short. So I'll be talking about the southern volcanic zone, and in particular these 6 volcanoes, so Nevados de Chillán, Antuco, Lonquimay, Jaima, Rica, and Osorno. So over many field seasons, hundreds of samples, mostly from Jaima, were collected, and all the samples were analyzed for major and trace elements, and then subsets were analyzed for U-series, beryllium-10, radiogenic isotopes, and oxygen isotopes. So I'm going to focus on 60 samples that were analyzed for uranium, thorium, protactinium, and radium, U-series disequilibrium, and also talk about some of the new beryllium-10 results. These were done by Jörg Schaefer, and he has invoked a technique a leaching technique to get rid of meteoric contamination. So the motivation for this study is in 2 parts. The first are early regional studies of the southern volcanic zone using work by Sigmarsson and Morris. And they show that the whole arc can be related by mixing between a common mantle source, somewhere over here, and a subduction component up here, where the beryllium-10 would be coming from the sediment, and radium excesses and uranium excesses would be coming from the altered oceanic crust. And this has basically formed how we have thought about metasomatism in subduction zones over the last 20-plus years, and particularly because the preservation of the radium signal indicates that the time between mantle metasomatism and eruption has to be less than 8,000 years. But this relationship is only based upon mostly single samples from individual volcanoes. So, which brings me to the second source of motivation, which is recent work by Rayleigh et al., which have found that at Volcan Jaima in the southern volcanic zone, it has been subjected to crustal assimilation. So this is an equaline diagram. So the line indicates secular equilibrium in the uranium-thorium system. And we can see that the JIMA data set is characterized by mixing between the least affected sample over here with the uranium excess and a crustal component on the equaline, which is similar to plutonic rocks that come from Lucassen et al. This data set is pretty unique because it represents 30 samples that have been measured for uranium, thorium, protactinium, and radium U-series disequilibrium, as well as some of the other analyses I said before, like major elements, trace elements, beryllium-10, oxygen isotopes, and radiogenic isotopes. So when we look at the crustal assimilation trend on the beryllium-10 diagram, we see that while it doesn't reproduce the whole regional trend, it does reproduce a significant part of it. So this led us to ask the question of whether the other volcanoes in the southern volcanic zone have also been affected by assimilation or some other process, and what this means about the regional trend and whether or not the timescales that we get from it can stay the same. So before I show you all my new data, this was the data prior to this study for radium-thorium disequilibria and uranium-thorium disequilibria based on the work of Sigmarsson. And again, this is for mostly single samples from individual volcanoes. But we see the story gets a little bit more complicated when we add multiple samples from each volcano. So now each volcano is indicated by different colors. So JIMA volcano is now in white. Osorno volcano is in yellow. Lonquimay is in red. Villarrica is in blue. Antuco is in purple. And Chillán is in green. And so the radium-thorium systematics is quite messy. And the reason we see this mess is because crustal processes such as magma mingling and mantle, crystal mush things happen on the time scales that are similar to the half-life of radium. So this would cause decrease in the radium excesses. And I also want to note that some of the volcanoes you can see have both radium excesses and radium deficits. And while we're still trying to figure out why this is the case, it could be related to melting of a cumulate body and such. So because it's really hard to tease out the Mantle signal using radium-thorium disequilibria, I'm going to concentrate the rest of the talk on uranium, thorium, and protactinium systematics. So here is the data again on the equaline diagram and protactinium, uranium, and uranium-thorium diagram. And I just want to point out that besides Lonquimay, which is in red and forms a tight cluster, all of the other volcanoes seem to have intravolcano trends, which would indicate some sort of mixing process. And I'll go into detail in the next few slides. So we think that Antuco and Chillán have also been affected by crustal assimilation, as shown by the mixing lines, and they seem to be mixing to an assimilant that is similar to the plutonic rocks that affect JIMA volcano. And the least affected samples from each of the volcanoes you can see have quite different chemical characteristics. For Osorno volcano, it also appears that it's mixing to something that's similar to the JIMA assimilant. However, radiogenic isotopes and trace elements don't seem to support this. So it's mixing to something and very similar to one of the samples that is erupted from Osorno, and it has near equaline compositions. And lastly, for Villarrica, on the equaline diagram, you see that the Villarrica array is nearly perpendicular to that of JIMA, and we think it represents three-component mixing between the least assimilated Villarrica sample and melts similar to those erupted from some of the small eruptive centers surrounding the Villarrica edifice. And these were shown by Hickey Vargas from 1989 and 2002. And we would predict that these small eruptive centers also have high protactinium excesses, although this hasn't been measured yet. But such a composition could be could be achieved by starting with a mantle in secular equilibrium, adding a subduction component, which would cause a protactinium deficit or a uranium excess, and then aging towards secular equilibrium over timescales of several 100,000 years, followed by a melting, which would create a protactinium excess. Okay, so in order to find out what's happening in the mantle, what we really need to do is to use the least affected samples from each volcano. And as shown, and this is shown by the black dots on each of the diagrams. So we've done some metasomatism and dynamic melting modeling. So any metasomatized source is going to be a mixture with a mantle composition, sediment melt, and an AOC fluid, which is somewhere way out over there. And in order to test the Sigmarsson regional trend, which calls for simple two-component mixing between a mantle and a subduction component, we've created a simple model where we have a constant proportion of the AOC component and vary the sediment melt proportion for each volcano. And these are all constrained using the equiline diagram. So you can see that the metasomatized source is quite different for each volcano. And then we can melt the metasomatized source using dynamic melting in order to reproduce the U-series activity ratios of the least affected samples. However, in order to do this, we must vary melting rate and the partition coefficient of uranium versus thorium, and the range seems quite large for what we might expect, which indicates that the simple two-component system doesn't seem to be the case at the southern volcanic zone. And also to note that the high protonium excesses that we get indicate slow melting rates, and this would mean that the radium excesses are only from melting and not mantle metasomatism. So this changes how we might think about timescales. So instead of time between mantle metasomatism and eruption being less than 8,000 years, it seems that the time between mantle melting and eruption is less than 8,000 years. Okay, so lastly, we're going to see how this affects the regional trend with all this new data. So on the right-hand side, we see all the new data from this study. And we're not able to reproduce the high beryllium-10, beryllium-9 compositions that we see at Rica and Osorno from the old data set. And instead, it seems that there is a bimodal population with most of the volcanoes falling at around beryllium-10, beryllium-9 ratio of 3. But then Chiana and Antuco are much lower. And we might be able to attribute these low compositions to a larger accretionary prism in the northern portion of the arc. So this means that the beryllium-10 rich sediment that's at the top of the slab has been scraped away. And/or we can attribute it to the aging post-metasomatism and pre-melting that I described for the small eruptive centers surrounding Rica. Okay, so these are the conclusions. So we've produced a new data set with uranium, thorium, protactinium, and radium for 50 samples in the southern volcanic zone, plus beryllium-10 and major elements, trace elements, radiogenic isotopes, and oxygen isotopes. Each volcano has an intravolcanal trend based upon assimilation or mixing processes in the crust or mantle. In order to do any sort of mantle modeling, we need to look at the samples that have been least affected by these processes. And also the slow melting rates based upon the protactinium excesses indicate that the radium disequilibrium is really a function of melting and not of slab fluid addition. So this leads us to the last conclusion that with denser sampling and also new analytical techniques, the iconic relationship that's been used to describe beryllium-10, beryllium-9 versus U-series relationships for the southern volcanic zone doesn't seem to be valid anymore. So we can't really use a two-component mixing to explain the whole arc, and each volcano needs to be evaluated on its own. And these results have implications of how we think about subduction zone processes, such as mantle melting and mantle metasomatism, and also the time scales. And these might be important input parameters in the geophysical models that you've seen before. Thank you.
We have time for a quick question.
I have a question. Yeah. if your beryllium-10-9 isotopes correlate with other trace elements that are sort of good indicators of sediment fluids or sediment melts?
Okay, so the question was whether beryllium-9 varies with any other trace element indicators, and I focus more on the U series, so there's going to be actually a talk by Steve Turner in the Mantle melting poster session, and I think if we look at them, then we'll be able to figure that out. Okay.
Thank you. So next speaker is Christina Walowski, Understanding Magma Formation and Mantle Conditions in the Lassen segment of the Cascadia Arc, Insights from Volatile Contents of Olivine-Hosted Melt Inclusions.
It is bright up here. Good morning. As Ikuko said, I'll be looking at I'll be showing the work we've been doing looking at the volatile contents of olivine-hosted melt inclusions to understand magma formation and mantle conditions in the Lassen segment of the Cascade Arc. So the biggest motivating question for this research stems from the fact that the Cascade Arc subducts some of the youngest and consequently warmest oceanic crust globally. And we're interested in how this really warm crust affects both the dehydration reactions in the slab and the melt production in the mantle wedge. We're going to try to answer this by looking at the volatile and trace element variations across the Lassen segment of the Cascade Arc in particular to see how this could relate to the amount or the composition of that hydrous slab component. We'll also look at how the Lassen region compares to the other segments of the arc briefly. As both Haiying suggested, their arc has been segmented based on tomography, trace elements, and isotopes. In particular, we'll compare to the Central Oregon segment. And lastly, we'll look at slab surface temperatures, which we've calculated using the newly developed water cerium slab thermometer to see what that can tell us about the melting processes that are occurring beneath the Lassen segment. So the Lassen segment of the arc is the southernmost active volcanism in the Cascades, with Lassen Peak erupting just about 100 years ago in 1915. Volcanism is the result of subduction of the Gorda microplate here, and fortunately for us, there are many cinder cones which have erupted primitive magmas, as primitive magmas can tell us a lot more about the mantle processes rather than crustal processes. These magma types are dominated by calc-alkaline basalts, which I will call CABs, and low-K tholiites, or LKTs, which are also commonly referred to as HEOTs in the Lassen region. Our sample set contains 7 cinder cones so far, and they range from Black Butte in the west, approximately 80 kilometers, to Round Valley Butte in the east, approximately over the arc axis, which is at Lassen Peak. So as I said, in this study we'll use olivine-hosted melt inclusions. We've analyzed just over 100 glassy olivine-hosted melt inclusions from cinder cone tephra, so the explosive eruptive deposit, which is believed to cool a lot more rapidly than, say, a lava flow would. We've looked at water and CO2, which we've measured on the FTIR, major elements, chlorine and sulfur, on the electron microprobe, and we did our trace elements on the laser ablation ICP-MS at Oregon State. First, comparing our magmas to others in the Lassen region. Here we have K2O versus silica on the left, and for every single one of our melt inclusions. And on the right, we have the average trace element composition for each cone, normalized to depleted Morb mantle. And we also show a typical LKT and typical CAB from the Lassen region. Coming back to the left, you can see that all of our samples plot on the least evolved end of these Lassen samples, and they also have high Mg compositions. And also you can see that there's 2 samples, these blue samples here, that plot in the low K field. But if you look at those same 2 blue samples in trace element space, you can see that they're elevated compared to that typical LKT of the Lassen region. And because of this, they're not traditional low K tholiites, and we'll consider them calc-alkaline basalt transitional magmas for the remainder of this talk. As I said before, we're interested in these cross-arc variations because they're believed to reflect this waning supply of slab fluids with both increasing distance from the trench and depth to the slab. Here we have a figure from Borg et al. 1997, which shows calc-alkaline basalts from the Lassen segment. On the y-axis, we have strontium over phosphorus normalized to primitive mantle, which is a slab fluid indicator of the slab component versus distance from the trench. And we see it, although the trend is variable, that the lavas with high strontium phosphorus are found in the fore-arc and the arc axis, and those with really low strontium over phosphorus are found dominantly behind the arc axis. Strontium over phosphorus appears to be an excellent indicator of the slab input. Here we have it versus barium over tantalum and strontium isotopes. This figure is from Borg et al. 2002, also from about the Lassen segment. And as you can see, that strontium over phosphorus correlates positively with other commonly used elements that indicate the slab component, such as barium over tantalum, positive correlation here, and inversely with strontium isotopes, which indicates the component has unradiogenic strontium, like the oceanic crust. And this variation is proposed to be due to a mixing of an isotopically depleted slab component with an enriched mantle component. But before we can compare our volatile data from melt inclusions to these other fluid mobile trace elements, we must understand their variations that are related to degassing. Here I have CO2 versus water for two of the cones in our transect, poison butte and cinder cone. And as you can see, these melt inclusions are trapping melts that have experienced variable amounts of degassing over a range of depths. So it's important to note that we must use maximum volatile or at least here maximum water contents, because they are most representative of that initial magma. You might also notice that there is some scatter deviation to the left of these open to system degassing paths, and that's likely the result of post-entrapment diffusive loss of hydrogen. Looking at other volatile contents that are more soluble than water, here we have chlorine and sulfur from poison butte again, but also a different cone from the transect. Here plotted against water, and you can see that chlorine actually shows little to no evidence for degassing with concurrent degassing of water. Sulfur, on the other hand, does show a degassing trend. This decrease in sulfur may also be due to sulfide fractionation, but the important thing to note is that we can only use our high sulfur values to be most representative, but that we can actually look at most of our chlorine values because they don't vary very much. Okay, so now that we have our volatiles sorted out, we can now compare them to the fluid mobile elements from these melt inclusions. Here we have chlorine over niobium and our maximum water versus cerium versus this slab fluid tracer and strontium phosphorus, and you can see that they correlate very well. Also, I've plotted enriched and normal morb here in these open and closed diamonds, and you can see that these Lassen, the melt inclusions from these cones in Lassen, appear to be some continuum between this morb-like mantle component and some very hydrous subduction component. And if you remember that decreasing trend in strontium phosphorus across the arc, this also confirms a decreased slab flux with increased distance from the trench. Now stepping back and taking this data to compare with Central Oregon, here we have data from Rashido et al. 2010. I have water versus silica and titanium. Now we're looking at calculated primary melt compositions, so they're calculated to be in equilibrium with Forstrite 90 or mantle olivine. And you can see that there are systematic variations with water, both in silica and titanium. Titanium varies as a result of differences in the degree of melting and source composition, where silica varies as a result in variation of source mineralogy. The important thing to note here is that not only Lassen and Central Oregon are showing very similar trends with these major elements and water, but they generally also overlap, with perhaps Lassen having slightly higher volatile contents, which could imply a slightly increased slab flux in comparison. Also, just to note, the transitional CABs really fall off this trend because they have much low water contents, and this could be consistent with their similarities to LKTs and may in fact be mixtures of two different mantle sources. To finish up, I'll be discussing our water cerium calculated slab surface temperatures. To introduce it, I have a figure from Cooper et al. 2012 showing how water cerium derived temperatures versus geodynamically modeled slab surface temperatures. And on the right, a figure from Rashido et al. 2012 showing both temperature and water cerium and how it correlates with fluid mobile trace elements, here barium over lanthanum. And you can see that not only do our water cerium derived temperatures agree with temperatures from geodynamic models, but that the cascades are on the fairly hot end, here calculated at about 800 degrees C. This is the slab surface temperature. What's also interesting is because it's so warm, compared to others worldwide, we do see lower concentration of volatile and fluid mobile elements. Now looking at the slab surface temperatures calculated from our calc-alkaline basalts in the Lassen area, you see here on the, on the left we have slab surface temperature all calculated at 90 kilometers, which is the depth to the slab in the Lassen, below Lassen Peak. And on the right we have now water cerium in the slab component, which is calculating using methods from Cooper et al. 2012. You can see that these temperatures overlap with those previously calculated in Central Oregon, which was at about 800 degrees C, and that you also see that some of these magmas have much lower slab surface temperatures than compared to other parts of the arc. And these correlate also, here we have strontium over phosphorus on the x-axis, with these magmas that show the highest slab flux. Here I now have the calculated slab surface temperatures adjusted for depth. Here we have depth versus temperature in our water cerium slab surface temperatures plotted with modeled slab surface temperatures provided to us by Ikuko Wada. She made these thermal models for each segment of the arc. Here I have the models with a mean depth of decoupling of both 75 and 85. First, looking on the right to Central Oregon, you can see that the temperatures calculated using the water cerium ratio overlap very well with the modeled slab surface temperatures. Lassen, on the other hand, agrees fairly well, but has slightly lower temperatures than are expected from the modeled temperatures. And lastly, coming back to the initial question of what does happen to dehydration reactions and melting in this really hot subduction zone, I've superimposed the phase stabilities of a metabasalt from Schmidt and Poli 1998, showing the breakdown of important hydrous phases, such as amphibole. I'm sorry if it's a little hard to see, but what's the most important thing to note is that all of our slab surface temperatures from both Central Oregon and the Lassen region plot at or above this Morb plus water solidus. These results imply that we either see evidence for the physical melting of the altered oceanic crust, or that these phases are behaving metastably, these hydrous phases are behaving metastably and breaking down at slightly higher temperatures than would be expected from these equilibrium experiments. Okay, so in conclusion, the geochemical variability in calc-alkaline basalts in the Lassen region is related to the amount of this hydrous subduction component mixed with an enriched mantle source. The correlations of volatiles with strontium phosphorus imply a decreased slab flux with increased distance from the trench and depth to the slab. The compositional trends are similar to those found in Central Oregon, with perhaps the Lassen region having slightly higher water contents, indicating a slightly increased slab flux. And lastly, that our slab surface temperatures do correlate with the abundance of fluid mobile trace elements, and that the temperatures calculated from this method plot above the Morb plus water solidus, implying that we either have slab melting or that the hydrous phases, are behaving metastably in the altered oceanic crust. Thanks.
We have time for a question.
Yeah?
Just a quick comment that an alternative interpretation of your samples being shifted to higher temperatures off the Morb solidus would be that they lie directly on the water saturated solidus. So you're seeing melting of the mantle above the slab.
Yeah, or I guess you could also say that most of that hydrous flux is coming from the mantle that is below that altered oceanic crust.
Thanks. So next speaker is Hitomi Nakamura. Generation of adakites in a cold subduction zone due to double subducting plates.
Thank you. I'd like to talk about generation of adakites in cold subduction zone due to double subducting plates. Adakites has been found in various tectonic settings since firstly reported as a product of slab melting in Adak Island by K. 1978. Recent studies suggest various occurrences and sources for generating adakites, such as slab, mantle, and lower crust for their genesis, for their origin, and many mechanisms has been suggested. I'm from Tokyo here, in central Japan, where two oceanic plates subduct beneath Eurasian plate and North American plate. The Pacific plate subducts from east, and Philippine Sea plate subducts from south, with a shallow dipping angle, and overlaps the subducted Pacific plate. These two slabs absorb small heat from the mantle, and resulting in very cold subduction zone. In this tectonic setting, we have found adakites in Backarc region in central Japan. By using strontium yttrium diagram, adakites can broadly identified as a pinkish area. In our samples, about 30 rocks marked with a red circle strictly meet the criteria of adakite, while other volcanic rocks marked with gray circles are plotted in the blue region. Note that pinkish studs undifferentiated rocks also meet the criteria of adakite. This is silica and magnesium diagram. Adakite and undifferentiated rocks both are on the trend, fractionated with olivine and pyroxene, plagioclase, magnetite, and amphibole, which are contained in volcanic rocks. Whereas primary magma is thought to be generated in the gray area, gray region, at 1.5 to 2.0 gigapascal with a water-saturated condition, below 1200 degrees C, suggested by this study, as suggested by Farman and Grove 2004. We also found co-genetic signatures among adakites and undifferentiated rocks based on trace element and isotopic compositions. The composition isotopic ratio of adakites are almost the same with that of undifferentiated rocks, and more enriched than MOB, which indicating that their origin is not a MOB or a MOB-like source mantle. Next, we will discuss the genesis of these undifferentiated rocks having adakitic signature after showing the thermal structure beneath central Japan. Left figure shows how two slabs overlaps in the central Japan, and the geosam is thought to be very cold due to double slabs, which make the corner floor to be more stagnant. This cold environment makes deep water subduction and serpentinized layer dehydrate at 7.5 and 3.5 gigapascal for Pacific and Philippine seaplate, respectively. Seismic studies also support the existence of a serpentinite layer, which contribute to generate a magma, a primary magma, by bringing water and elements. This water is contribute to generate primary slab-derived fluids. So next, we constrain fluid properties as follows. This figure shows a systematic spatial variation on isotopic ratio for Japanese wall volcanoes, which can be explained by the mixing between depleted mantle and slab-derived fluid. Based on this systematics, we can calculate the parameters concerning slab-derived fluid against mantle. In addition, fluid composition can be calculated forwardly by using ODP data before subduction and element mobility determined by high-pressure experiments. With these parameters, slab fluid composition and fluid metasomatized source mantle composition can be forwardly determined. From this green line, primary magma generates. Now we know this here, source mantle composition where a fluid induces a melting. The melting can be described by the 3 parameters: melting degree and proportion of garnet and spinel lazurite. Here we call beta garnet and partition coefficient. Melting degree and partition beta garnet correspond to the melting temperature and depth of melting. By using partition coefficient and studied by high pressure experiment and lattice strain models, we can obtain the primary magma composition by using 2 parameters, melting degree and beta garnet. By optimizing melting degree and beta garnet to the observed composition of volcanic rocks for beneath each volcano, the melting temperature and the depth can be determined for each volcano. And the left figure shows red line, black and red line corresponding to predicted and observed melt composition, which coincide well for each volcano. And light figure shows misfit content map for each volcano. And the solution is constrained fairly well. As a result, the best fit solution is below for volcanoes like this. On average, about 10% of garnet lazurite melting explains the observed primary magma. This figure shows, this is a PT diagram, and the green curve is our result in this study. And the green curve is the estimated thermal regime. Our obtained melting condition give a tight constraint around here, 2 gigapascal and 1000 degrees C. And in addition, being aided by numerical studies, the surface temperature of subducting 2 slabs, Pacific and the Philippine sea plates, also can be constrained around here and here. Now, we obtain the thermal regime as a green curve with 2 peaks and having 2 minima. This is some regime beneath central Japan in the west-east section. The Pacific plate subducts from east, and the Philippine Sea plate subducts from perpendicular to the screen. And the melting occurs in the mantle wedge over Philippine Sea plate. Consequently, low melting degree around here of dominantly garnet lazurite with high fluid flux from Pacific plate and Philippine Sea plate is responsible for distinct compositional signature with Adakite. This is summary, and the main conclusion is melting temperature fatigue condition can be determined precisely from trace element and isotopic composition of volcanic rock by estimating hydrous source mantle composition with slab inputs. As a result, we obtain a small melting degree where double slabs overlap and large contribution of garnet lazurite involving in melting. And also we have found Adakites in central Japan as a product of high fluid flux and low degree of garnet lazurite melting in cold environment due to double subduction. Thank you for your attention.
We have time for a couple of questions. Yes, Tim.
Very nice talk, but one of the things I noticed is that the solidus that you had on there, vapor saturated, was at 1,000. Turns out that the solidus that we have is
800
degrees. And also we measured the melt percentages near the solidus, and your temperature estimate, 10% melting at 1,000 degrees, is the amount of melt when the solidus is actually at 8.
Maybe this figure is like you suggest. You mentioned about this 800 degrees for melting. Our study only gave a strong constraint for depth due to trace element signatures. So yes, melting and also melting small melting ring about 10% gives the how to say distance from the wedge solidus. So it's okay if the melting degree is lower than this 1,000 degrees.
Another question? Yes. Can you say it again?
Can you also explain the major element?
Major element. Oh, yeah. Oops. Should I do this one? Oh, thank you. Major element. Yes. We have already checked. Sorry, I have not good figure for. I have not good figure now.
Maybe you can show him later.
Yeah. We can discuss later. Sorry.
Thank you.
Let's thank all our speakers again. And thank you all for coming. Just remember our posters will be tomorrow morning. Please stop by.